Hi, I am Rohit, and I will be presenting the paper Understanding when Spatial Transformer Networks Do Not Support Invariance and What to Do About it. The question I want you to keep in mind during my presentation is, can we achieve invariance to spatial transformations by applying spatial transformer modules on CNN feature maps instead of the input image? Before I start, a quick recap of the spatial transformer. The spatial transformer was designed to help CNNs be invariant to image transformations by learning a canonical pose for the input images. It consists of a localization network or LOC that learns a set of transformation parameters and a spatial transformer or ST block that warps the input image according to the transformation parameters. Now, the authors of STN suggested that these ST modules can be placed anywhere in the network, including transforming CNN feature maps. This can be beneficial because complex features can help to learn better transformation parameters. But does transforming feature maps undo the transformation of the input image? In other words, does it make the network invariant to input image transformations? This is important since several works apply STs on feature maps without providing justification. In this paper, the authors provide intuition why applying STs on feature maps will not always make CNNs invariant. To validate the theory, they conduct many experiments using different configurations of the spatial transformer to better understand when invariance is learned. Let's go over the insights presented by the authors. The first is regarding shift in the channel outputs. Consider the first input image containing the data M. It is passed to a CNN gamma, which produces two output channels. The first channel is a W detector, and the second channel is an M detector. Therefore, we don't see any activations on the first channel, but we do see an activation in the second channel. Now let us draw a 180-degree vertical flip on the input image and pass that through a CNN. We now see that the first channel activates while the second does not. Simply applying the inverse flip on the feature map is not going to create the same output as passing the original image. In fact, no spatial transform can make the two feature maps the same. So achieving invariance by transforming feature maps is not possible. The second insight is that receptor fields are not invariant to transformations. For example, when we scale the input image, the CNN filters are going to be looking at different input regions, and therefore we cannot guarantee the same outputs even after inverse scaling the output. The one exception is translation. Since CN is a covariant with respect to translation, STs operating on feature maps can support invariance to translation. The key design choices that the authors make, and which they also validate through experiments, are 1. Transform the input image and not the feature maps, and 2. Share parameters between the localization network and the mainstream classification network as a way of increasing the depth of the localization network. The authors tested 5 different architectures to understand which ones learn invariance. The first is STNC0, where the localization network and ST are placed at the beginning and we transform the input image. In the second, STNCX, the localization network takes a CNN map from the classification network as input, and the ST transforms the feature map. This architecture does not support invariance. In the third, STNDLX, the localization network is made deeper by duplicating X convolutional layers from the classification network. It is conceptually similar as the first one, but is deeper by X convolutional layers and enables comparison with the second. In the fourth, STN-SLX, the localization network is again made deeper, but now it shares some parameters with the classification network. Lastly, STN-L0123 is proposed, where localization networks are added at different depths. Each LOC predicts a residual transformation using more complex features. The predicted transformation parameters are remembered and composed in successive iterations and then used to transform the original image to preserve image quality. To understand how the forward pass happens, consider the third example, STN-DLX. Here, the input image is first passed through the purple X-convolutional layers and then through the localization network, which predicts the transformation parameters. And then that is used to warp the input image, which is then fed through the green convolutional layers, which performs the classification of the input image. The authors conducted many experiments, but here I present what I feel are the most important. First, they constructed the MNIST-R dataset by rotating every image in MNIST by a random amount from -90 to +90 degrees. The metric used to evaluate is the average standard deviation of the final angle, that is, after transforming the input image with the transformation parameters learned by the localization network. The expectation is that if the STN has learned a canonical pose, then the standard deviation will be small. First, we observe that STNC0 does better than STNC1, agreeing with the fact that transforming the input image is better than transforming feature map. Second, STN-SL1 and STN-DL1 both do better than C0 and C1 because they transform the input image and they use deep features. A final detail of why SL1 does better than DL1 is that sharing parameters between the localization and classification network makes sense because the features needed before and after transforming the input image are similar. Features like corners or edges are useful for predicting the transformation parameters and also for classifying the digit after transformation. Next, the authors construct the MLIST dataset by randomly placing the digit on a 60 x 60 cluttered background. The metric is the average standard deviation of the final distance. First, we observe that C0 and C1 perform similarly, agreeing with the theory that STNs can learn invariance to translation by transforming feature maps. Second, unlike in MLIST R, parameter sharing done in SL1 is not helpful because after transformation, the scale of the input image is drastically changed, and so we need a new set of filters for classification. This is the reason DL1 does better, as it uses a separate set of parameters for its localization and classification networks. The authors also evaluated the models on the Street View house numbers dataset, which is more challenging than MNIST. The metric used here is classification error. For their multi-depth localization network architectures, they found that SL0123 performs better than C0123, again showing that applying ST on feature maps is not good. Next is regarding depth comparison of the localization network. They find that transforming deeper features does more harm than good, and having no ST is better than having one at depth 6 or 8. In contrast, when you share parameters between the localization and classification networks, going deeper benefits accuracy. Lastly, it is also possible to apply the same ST iteratively, and the authors show that it is not a substitute for using deeper features, but can potentially help improve accuracy. The key takeaways are STNs cannot transform CNN feature maps in a way that enables invariant recognition for image transformations other than translation. Second, parameter shared localization networks remain stable better as they grow deeper, which has significant benefits on complex datasets. One limitation I thought of is that the authors have evaluated only for classification tasks, and I wonder how generalizable are the results to other tasks like correspondence learning. Coming back to the question for the class, the answer is that we can achieve translation invariance, but not for general offline transformations.